measure integration and analysis. Today we will continue with the solutions to exercises of sessions 1A. So we are able to solve question 1 to question 5. So yeah, let's see if we continue with question number 6 and then question 7 and then question 8. Alright, question number 6. Don't forget the textbook we are using. As let's measure integration and analysis by Sheldon Axley. Alright, so let's check question number 6. We have suppose f h to r is Riemann integrable and then suppose g so in the same interval is a function such that g of x equals to f of x for all but except finitely many x that belongs to our interval a comma b. So here's the question. Prove that g is Riemann integrable on then a comma b and then integral ab f. So g equals to integral ab f. So this is the point here. We have g of x equals f of x, but for all except finitely many. Okay, so let's see. Let's go straight to the proof. So don't forget, if f is Riemann integrable by the hypothesis, then for each epsilon greater than 0 there exists a partition P shows that the upper Riemann sum and then the lower Riemann sum is less than epsilon. So we have this fact. Okay, so for here now, let's define our partition carefully and then take note of some certain points. So let's see. Let's define the point at which let's define the point at which f of s is not equal to g of x. So for that, let's choose a small epsilon. So let's choose a very small epsilon greater than 0. Then x I minus epsilon and xi plus epsilon subset of our interval. So let's say for I equals to 1 dot k. So at this point, we say that our f of x is not equals to g of x. So then we can now look at the remaining point of our a comma b. So a comma b complements cut off the part xi minus epsilon xi plus epsilon for I equals to 1 to t. So this is the point where this is the point where f of x is equals to g of x. Also take note of this. At this point also take note that this is a disjoint, that is si minus epsilon xi plus epsilon intersect xj minus epsilon sj plus epsilon. So their intersection is empty for all I that does not belong to j. In other words, we defined a disjoint finite subintervals whereby those two functions are not equal. So we can now divide, let's divide another important thing now. Let h of x be g of x minus f of x. So then we have this. So if we are able to show that h of x is Riemann integrable, then that implies that g of x also is Riemann integrable. Okay, so then now define our partition. Let P be a partition of a comma b such that xi minus a, xi plus I as subset of a comma b. Okay, so then what we have so with that partition now, we note since f of x is bounded and g of x is bounded, that also implies that h of x is bounded. So since h of x is bounded, that means that there exists an m0 such that h of x is less than m. So with that now, we should be able to get the upper and the lower Riemann sum of h of x. So we can see, so where m is the sup or the maximum is what maximum, and I just use sup of g of x, comma f of x. Okay, so we are already considering the point at which f of x is not equal to g of x. So if f of x is equal to g of x, trivially that conditions we hold. So we are only considering the point at which f of x is not equal to g of x. So the upper Riemann sum of h over the interval a comma b of partition p will be bounded also. So let's say h. So this guy will be bounded by, don't forget the definitions, let me put it here, the definitions of upper Riemann sum. Definition of upper Riemann sum of a function, let's call it f, a function z a comma b is equal to summation the partition sj minus sj minus 1, then the sup of f over that interval sj minus 1 comma sj, h equals to 1 to n, depend on the n times partition you defined. So with that, so don't forget at the point where, so okay, so let's have it this way: the point at which f of x is not equal to g of x. So if we take the length of this, we are going to have 2e and then we have k's number. Don't forget, we define k numbers of these sub intervals where f of x is not equal to g. So we are going to have 2k in, and then we are going to have the maximum m. Okay, so this is the point where f of x does not belong to g of x. Alright, then so since this holds for all epsilon greater than 0, so similarly we can also define for, so similarly we can also bind the lower sum of our h so this also, okay, let me take this point. So this also is minus 17 to k, then this also is bounded by our lower Riemann sum L h of a of p. Okay, less than or equals to. So this is the point at which the function f of x and g of x are not equal. So if we add up these two, we're going to have, so we're going to have the upper Riemann sum a comma b minus 2m ke less than or equal to m2k 2m ke and plus LH AB. So then we have UH A comma B minus the lower Riemann sum less than or equals to 2m ke plus 2m ke, and this is equals to 4m ke. So hence we have proved we can make epsilon very small, and thus, so as epsilon tends to 0, very small, then our h of x is Riemann integrable. And then that also implies, so since we defined, since h of s equals to f of x, put it in mode, so g of x minus f of x, and since f of x is Riemann integrable and h of s is Riemann integrable, hence g of x also is Riemann integrable. So that's one part of the question. The second part, let me call it B. The second part of the question, we have to prove that the integral, so we want to show that integral abg is equal to integral abf. Okay, so let integral abh be equals to integral abf minus integral abg. So if we are able to prove this, then we are done. Okay, so by theorem 1.13 of the textbook we are using, so that is the bounds and Riemann integral. So we have these oaths for our h, so the bound of h by that theorem is less than or equals to the distance or the length of our mesh at which f of s is not equals to g of x, and that is equals to 2 ke, and then the sup of h of x. So this is by, okay, let me just write the theorem here. So by 1.13 we have integral ab of f is less than or equals to b minus a sup f a comma b. So we have that theorem. You can check the fixed video for that. So then we have checked the length of this before. So you can now say as, so we can take this to be our m, and then we have integral the mod integral ab of hn is less than 2 ke times the m, which is the maximum of g of x, comma f of x. So as epsilon tends to 0, for we can make epsilon very small such that our integral ab of h will be equals to 0. So, and then since integral ab of h is equals to integral ab f of x minus integral ab g of x, so since this is equals to 0, equals to integral ab f of x minus integer ab g of x. So this implies that integer ab f of x is minus integer ab g of x. And that concludes that proof. So if there's any question, you can drop it in the comment section. Okay, so we can now move to the next question. That is question number 7. Let's have it here. Question number 7. So we have suppose f a comma b tends to r is a bounded function for n positive integer. So we have let Pn denote the partition that divides a comma b into 2n intervals of equal size. So we have to prove that the lower Riemann integral is equal to the limit n tends to infinity and f the lower Riemann sum Pn a comma b, and then he asks us to prove the upper Riemann integral is equal to limit n tends to infinity the upper Riemann sum. Okay, so let's prove. So let's first start with the lower Riemann sum. So from the first video we have that that the lower Riemann sum, lower Riemann integral is equal to the sup over the partition Pn L of f a comma b and Pn. So and then that implies that this is greater than or equals to the lower Riemann. So that's by the properties of supremacy. So with that we can choose n for epsilon, for each epsilon greater than 0. Okay, so since this is we can actually bound this, and then we can go ahead to prove the first direction. So we are going to prove this by inclusion, we are going to prove the both direction. We are going to prove less than or equals to, greater than or equals to. Then we combine the two results, and that will give us the desired result. Okay, so if this holds, that means that we can write this to be L of A comma B Pn to be less than L of the lower Riemann integral. So I just flip this. So since this is bounded with this, then the limit as n tends to infinity L of f A comma B of Pn will also be less than the lower Riemann integral. So since our function is bounded by the hypothesis, since f is bounded, so that is one direction. Then the second direction we can choose, so we can choose epsilon for each epsilon greater than 0. This one, so I can see what's going on. So for epsilon greater than 0, so we can have the lower Riemann integral, which is equal to the sup over Pn L of A comma B Pn, but also this is greater than LF A comma B Pn. So we can choose epsilon such that for each epsilon greater than 0, so we can have it to be, so we know that there exists a partition PE such that this condition holds. L of f A comma B, the partition minus epsilon is less than equals to n of A comma B and we have this, and then this is also less than the sup. Okay, then what can we do here? Okay, we can have this, we have this condition n f the lower Riemann integral okay. So formally, without that epsilon, then we should, this condition should hold, the lower Riemann integral should be greater than the lower Riemann sum, but because of that epsilon we used, then that condition can hold for a specific partition. Okay, so now we need to define a refinement partition of this partition we defined. So let's say first let the mesh size, the mesh that is the size of PE be sigma. So then we can now choose, then for large n, so we have the partition of Pn for large n. You can see for large n we have, then for large n we have for n greater than, okay, then for large n, for all n greater than or equals to n, our Pn, partition Pn so the mesh for all n greater than or equals to n, the mesh size, that is the length of Pn, is less than partition, less than the mesh of partition P epsilon. So that means that so that means Pn is a refinement of Pe. But don't forget, we have this fact that if Pn, sorry, let me use, if A is a partition, is a refinement partition of A prime, then the lower Riemann sum A, B of A prime will be less than F A, B A. So the idea of this is that the more you refine your partition, the lower Riemann sum increases, approximate towards the function accurately. Then we have this theorem in the textbook we are using, that should be theorem 1.6 by theorem 1.6, 1.5, okay, particularly theorem 1.5. So the more you refine your partition, the more your lower Riemann sum increases. So with that fact, then we can see that this partition here, we can write it as what? So we can write it as LF A, B minus epsilon is less than or equals to n of A, B P epsilon, and then this is less than the refined partition A, B E of n. And don't forget, this also is less than, this also is less than, don't forget, this is equals to the sup Pn, okay. Now this also is less than the lower Riemann sum F of A, B, because this is the sup of this. Alright, then we can now have our n F of A, B, Pn is less than the lower Riemann integral. So from here we have this, and then we have this at the side. Lower Riemann sum is external. So then we can now take the limit. So for each external greater than 0 for large n, so we can see that these oaths are nf a comma b e of n for sufficient large n tends to infinity, because it's less than equals to the, so this also is greater than, or we can just combine it with the previous proved we have. Okay, this is for large n. Yeah, so for previous one we shown, so we have shown this equation star, which shows that our limit is bounded above. So we have shown from star we have limit n tends to infinity L of f a b Pn is equals to nf a comma b is less than. So with this condition, and then with this condition for each x greater than 0 and for large n, so we have our limit n tends to infinity of the lower Riemann sum equals to the lower Riemann sum. So similarly, we can also prove for the upper Riemann sum and the upper Riemann integral. So the next thing is to prove limit n tends to infinity the upper Riemann sum a comma b n is equals to the upper Riemann integral. So we know that for any partition Pn, for any partition Pn, and then we have uf a comma b, which is the infimum, this is the infimum over Pn of uf a comma b Pn, and then show by the properties of infimum this is greater than the upper Riemann sum. Okay, so another one, the upper Riemann sum is that one now? This is greater than or equals to the upper Riemann integral. Okay, so if we take the limit, since our function f is bounded, so this limit also is the holds. Since f is bounded. So similarly, for each epsilon greater than 0, there is a partition PE such that UF of PE that is the infimum, so that will be in the other way now. It's less than or equal to, sorry, common notation A, comma B of PE is less than or equals to the upper Riemann sum because of this epsilon. Now this is A, comma B. Okay, so if we find a part, if Pn is refined, we just choose large n, such that Pn, such that for all n greater than or equals to n, this mesh, the mesh of Pn is less than Pe. The reason why this is possible is because our Pn is given to be P minus A over 2n. So then we have that the upper Riemann sum, the more we refine our partition, the upper Riemann sum reduces. So Pn is refinement, is a refinement of Pe. Thus we have this UF A, comma B Pe. So this is greater than UF A, comma B Pn. Okay, and then this is also less than from this point, that's less than UF is epsilon. So if you also combine these two properties together, then we have our desired result. So for sufficient large n and small epsilon, then by this and this, so by 1 and 2 we have limit n tends to infinity, the upper Riemann sum Pn will be equal to the upper Riemann integral. Okay, so let's check one more. So the next question, okay, question number 8. We have suppose f function r is Riemann integrable. So we have to prove that this holds. So in proving this, we are going to depend on the previous proof, what we just proved now. A minus A over n equals to 1 n f a plus j A minus A over n. So to prove this, so let Pn be an equally spaced partition such that change of x is equal to b minus n for all positive integer n and I. So we are using J here for and for each Jn equals to 1, that's n. So that means that our partition Pn, we have something like this. The first partition A, and then the second partition will be A plus B minus A over n. I think let's divide this way. And that means that for each J, our partition, so we can have it as something of this form. Okay, so that means that the sub-intervals, so the sub-intervals can be of x0 common x1, then x1 common x2, so that's x n minus 1 xn. But here you notice that our sj's for j equals to 1 to n is a plus j changing x, this is changing x, and then this is equals to a plus j b minus a over n for our j equals to, I put j from 0, 1 dot n. So by definitions of lower Riemann sum, we have this n of Pn is equal to summation j equals to 1 n, and then the distance, which is sj minus 1, sj minus 1, and then the infimum f sj minus 1 sj. So you can see that this is actually greater than this is less than or equal to summation j equals to 1 to f, still the distance of our x j minus sj minus 1, the function of only the right hand side now, which is function of f a plus j b minus a over n. Why? Because of the definition of infimum. So we can also rewrite this and also write this as this is less than, because we did this other side now, this is less than summation j equals to 1 to n Then the distance of this for all the j's is given to be p minus a over n. So we have that, and then we have f of a plus j b minus a over n. Okay. Then also by definition of upper Riemann sum, and then by the properties of supremum, we can also have this condition as j minus sj minus 1 sup of f sj minus 1 sj. So this is greater than summation j equals to 1 to n sj minus 1 f of a plus j b minus minus a over n. So this is for the properties of the supremum, because this function only picks the right end of our sub intervals for each j equals to 1. So in the same vein, we can write our upper Riemann sum to be greater than or equals to j equals to 1 n. Sorry, the length of this over all j's is b minus a over n, and we have j equals to 1 to n sj minus 1. Sorry, that's repetition. That's f a plus j b minus a over n. So if we combine this result, and then we have, if we combine these two results, then we have b minus a over n summation j equals to 1 n f a plus j b minus a over n less than or equals to u f a comma b p of n less than n f comma b p of n. So by squeeze theorem, since we know, let's just take this part, we know that for large n, the limit of the upper Riemann sum, the lower Riemann sum is equal to the lower Riemann integral. That is what we just proved. And then the limit of n tends to infinity of the upper Riemann sum is equal to the upper Riemann integral. Alright, so by squeeze theorem, taking the limit as n tends to infinity, the limit as n tends to infinity, we have limit n tends to infinity b minus over n summation j equals to 1 to n f a plus j b minus a over n. That will be equals to the upper Riemann sum minus the lower Riemann sum, which is equals to the integral of a of f, and that is the same thing as FUF A, comma B, and F A, comma B. So this all follows from the squeeze theorem. So, and then this oath, and then we are done with our proof. So thank you for watching. Then we'll continue in the next video.